So, some applications of this then. What if the acceleration of a freely falling object is g? Freely falling is defined as the only force acting on it is the object's own weight, as in gravity is the only force. Weight depends on the object's mass and the gravitational field strength. We say that W is m times g. Weight is mass times gravitational field strength. We're already aware of that one. We could apply Newton's second law to that situation. Force is mass times acceleration. The force in that scenario is weight. So we're saying that weight is equal to mass times acceleration. Force is equal to mass times acceleration. So mass times gravitational field strength is equal to mass times acceleration. Well, there's mass on both sides. If we divide by mass on both sides, it will cancel out, leaving us with gravitational field strength is equal to acceleration. We write that in simples, g equals a. Well, what does that tell us? It tells us that gravitational field strength equals acceleration. Those two terms are measured in different units, newtons per kilogram and meters per second squared, but they have the same value of 9.81. It should be clear in which context, which units to use. Are we talking about Suvat equations and acceleration, or are we looking at forces and newtons per kilogram? When an object is in equilibrium, the support force will balance the weight. It will be equal and opposite. Like we saw in the table with the book on, the support force is equal and opposite. So if we had an object on a weighing balance, like a top pan balance or a Newton meter, it would cause the scale to read its weight. We would often configure the scale so it reads kilograms for our convenience, but really it's a measure of the object's weight. So if we took that top pan balance or Newton meter to the moon or Mars or wherever, then it would read a different number because it's reading the weight. We know that weight is different in different planets because gravitational field strength is different. We would need a different bit of apparatus to measure the mass. Classical physics, just as an aside, doesn't explain why inertial mass from F equals ma should be the same as gravitational mass from W equals mg. We defined inertia last lesson. We said the resistance of an object to being accelerated. So in Newton's second law, the m term is the inertia. So we would need a bigger force to get the same acceleration if the object has more mass, more inertia. There is no reason why inertial mass should be the same as gravitational mass, the amount that the gravitational field acts on the object's mass, the W equals mg one. Experiments show that they are identical, but we don't know why. That's one of the starting points of general relativity, that we can't tell the difference between standing on a massive object, for example the Earth. It should be identical to standing in a centrifuge that's rotating sufficiently quickly, like a wall of death, for instance. Here is our wall of death. So the guy is spinning around in a circle, and it's equivalent to if he were on the ground. So the motorcycle appears to stick to the wall, and he appears to stick to the motorcycle. But what it really is inertial mass and gravitational mass appear to be identical. So we consider an object of mass m supported in a lift by a spring balance. I've got a wonderful picture that I've done in Word there. There is a mass on a string, tension going upwards, and weight going downwards. Weight is the downwards force due to its weight mg, and an upwards force due to the tension of the spring balance T. The lift accelerates at acceleration a. So the force on the object, the net force will be mg minus T, and if it's the net force, that equals ma via Newton's second law. But if the lift is stationary or moving at constant velocity, it is not accelerating via Newton's first law. So acceleration is 0. We get mg equals T. The tension is equal to the weight. Well, that sort of makes sense, doesn't it? If it were a balanced force, then T equals mg. But what if the lift is accelerating? If the lift is in free fall due to gravity, the downwards acceleration is equal to g. So instead of writing mg minus T equals ma, we can write mg minus T, the resultant net force, is equal to mass times the gravitational field strength. But you notice we've got mg on both sides there, so the mg subtracts. We get T equals 0. If the object is in free fall, there is no tension read in that spring balance. So the spring balance would read 0. We call that weightlessness. So the gravitational pull is still acting on that object. There is still mg pulling downwards, regardless of whether it's in free fall. It does still have weight, but we call it weightlessness because it exerts no force on its support. So that object would be bouncing about like it were in a space station. In the same situation, if we stood a person on the floor of the lift, they would exert no force on the floor. So via Newton's third law, the floor exerts no upwards push. The person wouldn't have the sensation of weight. They appear to be weightless. So just to recap, they're not actually weightless, they just appear to be weightless because they don't feel a support of the floor or a support of the spring balance. Another application, rocket science. A reminder from GCSE, we could look at momentum, and we will in the next topic once we've done Newton's laws. But momentum is mass times velocity. We would say P equals m times v. We could rewrite Newton's second law, F equals ma, in terms of momentum. So momentum is mass times velocity, and resultant force is mass times acceleration. So all we need is to find out how momentum changes with time, and then we get force is proportional to the rate of change of momentum, how momentum changes with time. So we'd write that as force equals dp divided by dt. dp meaning the change in momentum, dt the change in time. If you are more comfortable writing a triangle for change in, please write a triangle, that's fine. If you are one of the maths students, will you be familiar that that's the differentiation of that? That's not on the physics spec though, you don't need to know that. You just need to be able to say change in momentum divided by change in time. Now if we substitute in P equals mv into that equation, that would give us force is equal to d, change in, mv, change in momentum, divided by dt, the change in time. However, mass is normally independent of time, so we could bring the m outside. If mass doesn't change with time, then the differential of it with respect to time is itself. So F equals m dv dt, change in velocity divided by change in time. But we know what change in velocity with respect to change in time is. The change in velocity over time is the acceleration. F equals ma. So all we've proved is that is the form of Newton's second law we're already familiar with. If we say force is proportional to rate of change of momentum, that is equivalent to what we're already familiar with. But in some situations, we will have to use that more complicated one, force is proportional to rate of change of momentum. And the situation where that would apply, well, that's the star where I've written it, isn't it? Mass is normally independent of time, but sometimes it's not. There are situations where the mass of the object changes significantly over time. I mean, we could look at a car. Technically, when you're driving a car, it uses the petrol and expels exhaust gases. But the mass of the petrol, even if you did the whole journey and used a whole tank of petrol, about 40 kilograms, is insignificant compared to the mass of the car, which is about a ton. So the change of mass is not going to be significant compared to the actual mass of the car. What about if we had a rocket though? The thrust of a rocket is dependent on expelling fuel in an explosion. So the mass is meant to change. We can't use the simple form of Newton's second law. At one instance, the rocket might have a mass m, so the resultant force will be given by resultant force F equals T minus mg, where T is the thrust of the rocket in this case. So we've got the thrust acting forwards and mg, the weight going downwards. We could easily see Newton's second law, ma, that the thrust of the rocket must be greater than mg, or the rocket won't take off. We won't get any acceleration. So what are plenary then? Can we state both forms of Newton's second law? The easy one, F equals ma, or the more difficult one, F is dp dt. Force is proportional to rate of change of momentum. we need to know both of these, and we need to be able to state both of those. They are applicable in different situations. F equals ma, to where mass is constant. F equals rate of change of momentum, to where mass does not remain constant. And we might need to use them in different situations as well. We'll look at that in the vehicle safety lesson, the lesson after next.